and good morning, Jiahong. All right, we seem to have, okay, hi, Sean. We seem to have most of you guys here. Let's go ahead and start, and we'll start from the announcements. Okay, nothing's new. The stream is there. The link for the Google Meet is there. Hi. And you know what? The ad codes are here. Okay, so you see, bullet number 3, the ad codes. So if you are waitlisted and you got in, try to find your ad code here in the list. You see that there are multiple columns. Find your student ID on the 学生学号 column. And then look left. That will be your ad code. Good. And today is going to be straightforward. In the first hour, we talk about the edge of the internet. In the second hour, we talk more about the mechanism, okay, the principle of how internet works in the core. Okay. So now, back to the first part. The edge of the internet, we know that the end systems belongs to the edge. We also know there's this thing called access network, which are actually links allowing the end systems to connect to the core. Okay. The end systems we'll talk a lot more about in chapter 2. Okay. In chapter 1 here, as an overview, we'll just talk a little bit more about the access network, this link allowing access for the end systems to the core. We will talk about these because they will not be talked about the rest of the semester, actually the rest of the book. Okay. So access network, and there are 5 kinds. The first 3, you heard about them. You probably use one of them at home, but exactly how they work behind, we don't quite know yet. So we'll be spending some time there going through each one of those. For the last 2, Ethernet and wireless, we use that a lot, and you guys probably know how they work already a little bit. So the videos for those parts are a little bit shorter. Okay, so let's start from the first kind of access net tech called the ADSL. Okay, originally just DSL. The first technology is called the DSL, Digital Subscriber Line. This is pretty much a legacy technology, which is building on top of yet another almost legacy technology called the telephone network. So let me draw your attention to the example at the top. Yeah, where the telephone network is, starting from here, the phone set, okay, where you make a phone call. So the signal is going to travel through the phone wire to the hub on the wall. There are lots of also wires behind the wall, connect you through the central hub in the building and then out on the streets. And there are quite a few cables buried underground, especially for Taipei City. And those cables take the phone calls to the central office. And inside the telephone company, there are these switches. They're switching the phone calls. And eventually the phone call reaches a friend that you're calling to. So this is the telephone infrastructure. And it has been there since, I think, late 19th century. But starting, I think, late 20th centuries, we want to do this. Okay, generating emails from our home PC and send that to a friend somewhere else, okay, connected also to the internet. Now, to allow this phone PC, a home PC, to connect to the internet, we borrow the telephone infrastructure, particularly the cables and the wires we have in the buildings under the street, so that we could send the data somehow to the central office of the data network providers here. And the way it works is this. Let's assume we're sending an email to a friend. So that email is going to go and reach the DSL modem first. So DSL is the name of the technology. Modem here is actually modulator and demodulator. Okay, the first few letters combined. So what it does is, hey, email coming from your PC is in digital form. It's going to be converted to the analog form, so it can go on this cable here and multiplex potentially with analog phone calls coming from the phone set. So these together can travel the cables and reach the central office of the service provider. And by the way, very oftentimes the telephone service provider is also an internet service provider. Now, once they reach the central office, this big box, DSLAM, it's DSL, I think access multiplexer, okay? Whatever it's called, what the functionality of this yellow box is simply, first, split the analog signals. Some of those could be analog voice for the telephone network. It will go on this way. Some of those are for the internet. It will go on the other way. And before this analog signal can go out to the edge server, DSLAM also demodulate the signal from analog back to digital so that it can travel the digital data network. You can imagine vice versa. Your friends send an email back through the edge router and reach the big yellow box, and that email gets converted to the analog form and multiplex with the phone calls together, traveling the cable, and finally reaching the household. First, go through the splitter. If it's phone call, go this way. If it's internet data, go this way. Now, at this point, the internet data is still in analog form, so modem here demodulate from analog signal to digital, and therefore you get to read your friend's response. Now, if you think a little bit more about the yellow box, what it does is essentially what the blue and the green box are doing combined. Modulating and demodulating. Multiplexing and demultiplexing. What is a little bit tricky there is so that how do we do the modulation right, and how do we do the multiplexing so that the voice and the digital data will not interfere with each other. And that is done and achieved by splitting the frequencies of the EM carriers. So what how we are sending data or in analog or digital form is that we are modulating these signals onto the EM wave carriers. So we modulate the analog voice to this frequency band of the carriers, and upstream data to this frequency band, downstream data to this frequency band, and they are mutually exclusive, therefore they won't be interfering with each other. Okay, so phone is going through the 0 to 4 kHz frequency band, and upstream data 4K to 50 kHz, downstream data 50 kHz to 1 megahertz. So you see that the downstream data is using a wider frequency band, and so not surprising, upstream bandwidth only 1 megabits per second, and downstream we get 8 megabits per second. The last about DSL is this link here. Yeah, this is one link per household. This is very dedicated, okay, between the central office to the user. All right, and you know what? DSL was the original name. In the video, you just saw that the downstream bandwidth can be 8 megabits per second, and uplink only 1. So the bandwidths between downlink and uplink are asymmetric, so they are not symmetric. That's why DSL is also called the ADSL. The A stands for asymmetric. And now let's go on to the cable modem. I would say that probably in Taiwan, cable modem is a lot more popular than ADSL. Oh, and the second access net is cable modem. A little bit similar to DSL, it's also for residential access. And unlike DSL, which is exploiting the telephone infrastructure, cable modem there uses the cable TV infrastructure. Yeah, you see, we also have lots of wires behind the walls leading to a central office, leading to the cable company. That's how we receive the TV programs. So, cable modem here, exploit that existing infrastructure. What's nice about the cable modem is this. The bandwidth available, it's also asymmetric, where you see the downstream bandwidth and the uplink bandwidth different. In cable modem, wow, lots of downstream bandwidth, 30 megabits per second, but very limited upstream bandwidth, only 2 megabits per second. If you judge based on only the amount of downlink and uplink bandwidth from cable modem and compare it to DSL, you'll see, whoa, cable modem wins, obviously. Yeah, for DSL, this is only 8, and this is only 1. But you want to be careful though. These cable fibers attaching household to the cable company, they are shared access links. Unlike DSL, these telephone wires are dedicated access. That is saying, oftentimes a cable company will set big cables, center cables from the center office to a neighborhood. And there's going to be a splitter that splits TV programs and across hundreds and maybe thousands of households. Yeah, if you use cable modem, sending data, your data and all your neighbors' data will be multiplexed on that cable and to the central office. That cable there is not dedicated, it's shared. So even though the bandwidth is higher, but you can be competing potentially with all your neighbors. And it really depends on how many people are subscribing to the cable modem service in your neighborhood. That determines really the quality of your internet access. To illustrate, let me show you this example where we're connecting hundreds and thousands of households together through one major pipe to the cable company. And inside the cable company, you see often lots of these video servers, and stored on these video servers are the TV programs. So the cable head will stream these videos down this way. Gets splitted here, 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 here. Okay, depending on what each of the household is requesting. Okay. Occasionally also, from the household, there could be some control messages being sent, for example, to switch channels. Okay, for example, to turn the TV program off. Now, if you have the cable modem installed at home, the infrastructure is going to look a little bit more extended, but most of the extensions are inside the household as well as in the central office of the cable company. Yeah, I know, if you look at this picture here, you see, very familiar, right? Just like DSL. If there's signal coming in, the splitter here will check. If it's TV program, it will go on this way. If it's data, internet data, it will go on this way. And the cable modem will convert it to the format that's readable from our PC, and therefore you read the message from your friend. And similarly going out the other way, right? So your message will go out from the household and through the shared pipeline to the cable company. And inside the cable company, there is this big multiplexer and modulator that's doing the right thing so that your internet data goes on to the rest of the internet. Okay. And your friend sees your message. Now, be careful here. There's only one cable here. If there are messages coming from this other household or this other household, they will all get merged onto this cable. Now these messages coming from the household, they will share the same channel and compete for the bandwidth there, unfortunately. Another thing that you might find surprisingly similar between cable and DSL is this: how we are multiplexing the original infrastructure networks data as well as internet data. And this is how cable modem is doing it. These first few channels are video, data, and last one, control. The channel towards left, lower frequency. The channel towards right, higher frequency. So essentially what you're seeing is that the entire frequency band allowed on a cable network are divided into some subbands. Okay, so 1 to 6 are for videos, which are the TV programs. 7A, in this example, are for the internet data. And then these control messages, such as switching to a different channel, to a different TV program, is only just one subband. Right? And so they kind of run on frequency subbands that are not overlapping, completely separated, so that they would not be interfering with each other. Okay? So that technique is formally called frequency division multiplexing. Okay, so we kind of cut the entire frequency band into non-overlapping subbands, division over frequency, hence the name. All right, now you also know, right? You can actually infer ADSL is also division, frequency division multiplexing. Remember the original phone call within a certain frequency band, right? Downlink and uplink data, yet two other subband in the EM frequency band. All right, that was the similarity between ADSL and cable, but there's a major difference. Cable, share medium. ADSL, dedicated. So ADSL, although bandwidth is lower, but it's dedicated. Cable, bandwidth higher, but many households might share. Okay, and it's because of in cable modem, you are actually sharing the access link to the internet, so that the cost can be a little bit lower. Okay, and that's why most Taiwanese households prefer subscribing to cable modem, because they are actually, to me, a little bit too cheap. Next one, Ftth. Okay, this one is expensive, and you'll see here now why it's expensive. Fiber to the home. This is the third access net technology. Unlike the previous two, where we kind of exploit certain existing infrastructure, telephone network or cable TV network, this one here builds its own network. And because the cable are all optic fibers, so it's called a optic network. And it's essentially the internet service providers, if they want to allow users to access internet using FTTH, they will have to go out there and build these optic links into the civil infrastructure. So there are physical contact, through some cables between the central office to home. And so you see in this example, it's very clean, between the central office to each household, just optic cable. Right. The only slight complication and boxes that are a little unfamiliar to you are these. First, optical line terminal. So this is a dummy device. What it does is just to collect signal and then convert them into digital bits. Okay, so that these internet data can go on natively through the edge router and out to the internet. Now, what's a little bit more interesting is this box, the optic splitter. We've seen this term, splitter, the third time. Yeah, at the physical level, these splitters are essentially the forwarders or the switchers. Okay, so signals gets forwarded to the right destination at this point. And signal gets multiplexed also, so that they can go on further upstream. Okay, so splitter plays the role of demultiplexing signals so that it reaches a particular household, or multiplexing signals so that it goes to the central office. So its role is a little bit like the routers or switches at the core of the internet. So Optic Splitter here is a very important device for the optical network. In this example, we see there's only one level of it. In practice, there could be multiple levels, so that you could have a regional optical splitter, and then you could have another splitter here inside the building in case there are multiple households in your building, okay, also subscribing to the optical service. Now, these splitters, depending on the mechanism that's running in it, okay, depending on the design, could work differently. Okay, so two typical architecture for these splitters are these, PON and AON. So passive optical network. What it meant is that what's being done here is very straightforward. You just have mirrors so that you can reflect signals so that they go on the right direction to the destination. There's no signal amplification. But if you use active optic network splitter, yeah, these signals get splitted and amplified before they get passed on further. That is very necessary in case there are multiple levels of splitters along the way. As a signal, as it travels longer distance, even though it's optic signal, it's still decay. Okay. Now, in FTTH, yeah, the downstream or upstream bandwidth vary, but essentially the maximum capacity is much higher than the cable modem network, than the DSL network. Okay. In Taipei, very typical, you subscribe to services that's downlink 100 megabits per second, uplink 40 megabits per second. Okay. If you have special need, for example, if you are hosting web servers, then you might subscribe to 100 megabits per second downlink and 100 megabits per second uplink as well. Okay, so it can be symmetric, it can also be asymmetric in terms of the bandwidth in going in different directions. So essentially much higher rates, and it really depends on how much you can afford. Right? And nowadays these fibers can also carry telephone or television services. Okay, think about video on demand. So that is to carry TV programs through FTTH. And digital phone, okay, IP phones are one example. The trend is going towards that's just move to FTTH and then abandon the older legacy technology such as telephone, such as cable TV. So all content, including data, are transmitted over the one and only internet. One ring to rule them all. All right. So now, thinking from a user's perspective, okay, having higher bandwidth, okay, having dedicated access, okay, you feel it's okay to pay more for such as internet access. So this is thinking from the user's perspective, but thinking from an ISP provider's perspective, you need to charge the users more. Why? Because all these optic fibers, they are new, unlike the phone cables that are already buried underground for years, for decades, in fact. Okay, unlike the cables, okay, network, they are also there for decades. Okay. To build this optic network there, active access network there, there's also a lot of cost to try just to build the infrastructure. Okay, in addition to all these splitter equipments. Okay, so those are all new investments. All right, but gradually, so urban areas and probably some of the rural areas, there'll be optic access networks all around, such that we could enjoy high bandwidth and dedicated access. So we could do audio, video, web, or any other applications we want to do from home or coming to home. Now the two other kind, Ethernet and wireless, they are lighter and they're actually more familiar. Ethernet, very short video. The fourth network access technology is Ethernet. Now this is something that we're very familiar with. All we need to do is to purchase one of these Ethernet switches, connecting our computer through the Ethernet cable to it, and this guy is connected to the edge router. Then data can go out and in from the internet. Such a network access is typically used in companies and universities, okay, as they have direct access to the edge router. For households, we usually don't have access directly to the ISP's edge routers, okay? So even though you're trying to connect your end systems through Ethernet cable to a switch, but that doesn't mean your access network is that Ethernet you're using. Be careful. Now, the rate these Ethernet switch is operating goes from 10 megabits per second 10 years ago all the way to nowadays 10 gigabits per second. But I think typically people use an Ethernet switch at this speed, 1 gigabits per second. And nowadays it's actually dedicated upstream 1 gigabits per second and downstream also 1 gigabits per second. 10 gigabits per second Ethernet is a little bit limited, and only those companies who are, for example, hosting a lot of data, then they need 10 gigabits per second Ethernet, particularly video providers. All right, quite straightforward. You see here, much higher bandwidth and dedicated. Now, what about wireless? This is the last access technology. It's called the wireless access. That's just how I refer to both of these wireless access technologies in a general term. Okay, the common characteristic is that all the devices, okay, on the same channel will share access. So the way it works is this: devices sending wireless signals. It's picked up by the wireless base station and then passed on to the edge server and then further on to the internet, and vice versa. So these base stations, in the context of Wi-Fi in particular, are also called the access points. Now a little bit more about Wi-Fi. AL2.11b or G. This is actually a pretty old standard. I'm pretty sure that all of us are using AL2.11 at least N. Okay, so that's Wi-Fi generation 4 in another way. The bandwidth with Wi-Fi generation 4 is already close to 400 megabits per second. Okay, and the frequency band is no longer just 2.4 gigahertz, but also the 5 gigahertz band. That's why when you purchase a new Wi-Fi AP, you see that, hey, a lot of times when you set it up, you see two channels, one for 2.4 gigahertz, the other for the 5 gigahertz. The next major generation is Wi-Fi 6, which operates also on both 2.4 and 5 gigahertz for backward compatibility, in case you're still running AL2.11b or G. For Wi-Fi 6, the bandwidth actually go up this high, 900 and plus megabits per second. Really nice. I think in the next generation, that's called the AL2.11ad. Yeah. For this version of Wi-Fi, it's gonna operate at this frequency band, 60 gigahertz. It's super high frequency, super high data rate. In fact, 5G is also aiming at this frequency. So bandwidth is going to be a lot higher, but you see also that the transmission is very directional, a little bit sensitive to the antenna design, okay, and very sensitive in case there's mobility. All right. Wi-Fi, interesting development there, AL2.11ad. The last one Okay, wide area wireless access actually meant, so 1 megabits per second, this is for 3G. Okay, for 4G we get slightly more than 1, sometimes go a few megabits per second. With 5G you get easily tens of megabits per second and sometimes very close to 100, but only downlink. I have not yet seen any sort of measurements about 5G uplink bandwidth. It would be very interesting to know if you find any. Okay. But although these bandwidths we're talking about, downlink, uplink, it's increasingly higher and higher even for wireless access. But be very careful. As opposed to Ethernet, as opposed to optic, wireless is, after all, shared access. So these 400, 600, 900 or close to tens of megabits per second bandwidths are shared among all the users. And nowadays we are probably connected to the network more through wireless access network, okay, than the wired one. All right, so wireless access, the bandwidths available are actually substantially lower than the wired access network. On top of that, we are sharing the bandwidth. And on top of that, it also depends on where we are to the AP. The farther we are, the bit error rate higher, the effective bandwidth is even lower. Okay, so wireless, it's convenient. We can connect to the internet as we're moving, but the available bandwidth really substantially lower. Good. So 5 kinds of access network technology. We're not yet done. Before we talk about the physical media, the cables, okay, that connect the end systems to these access networks. Let's summarize everything, because nowadays how we access network can be a little bit more complicated. We could be using combinations of these access network technologies. To sum things up, we've talked about 5 access networks: DSL, cable modem, and the very powerful FTTH, the optical network, to allow all the data, not just text-based, but audio, video data, to traverse. And it's replacing the traditional phone network, replacing the traditional cable TV network. We also talk about Ethernet access and the very, very popular wireless access. Now, all these 5 are access network technologies. These 3 definitely use a lot more for residential access. These 2 definitely use a lot more for institutional and mobile access. But nowadays, in a household, as the demand of using internet is on the rise and there are a lot more end systems are connected to the internet at home, having just one particular access network to enable multiple machines to go online at the same time is really challenging. So we have a hybrid access network in a way. In this example I'm showing, this is very typical home setting. Cable modem here is to access to the internet for the household entirely. But after the cable modem, we have what? An Ethernet switch here, okay, which is also called a router, which also runs the firewall functionality. This guy here would allow, for example, these PCs to connect through Ethernet cable to it. Yeah, these PCs are accessing internet using Ethernet switches. And the switch here can also connect to a Wi-Fi AP, and so that these laptops are accessing Ethernet through Wi-Fi. So in just this example, you have devices accessing the internet through different access net technologies. And be a little bit careful when I ask what is the access network for a particular computer. It can be relative, right? So this guy here is through Wi-Fi, this guy here is through Ethernet. But if I ask, how is this household accessing the internet? Yeah, the access network used by the household entirely is the cable modem. All right. Next, let's talk about the cables. The video is a little bit longer, about 8 minutes. Be patient with me. Here we're going to switch gear a little bit, but still about access network technologies. And so far, if you paid attention, each of these access net technologies operates on some sort of mechanism or protocols. They also operate with assumption on there's a companion physical media. This is important, just like the protocols are important to achieve a certain expected performance, typically achieving a really high bandwidth. Okay. Now, so let's go over these physical medias that work side by side with each of these access technologies. Now first, let's define some terms. Bit. These bits are propagated between the transmitter and the receiver. And between the transmitter and the receiver, whatever the media is called a physical link. And these links can be wired. There's a special term called guided media for it. If it's wireless link, then it's unguided media, meaning that the signal might just go propagating omnidirectional everywhere. Okay. As opposed to guided media, there's usually a copper wire or an optic fiber that the signal kind of just follow and being guided to travel through the physical media. Now, there are 4 kinds of physical medias we'll be talking about. First is twisted pair, and this is one of the commonly used cable for Ethernet. Cat5, this is very old for Ethernet that's 10 years ago. Nowadays, I think we're still using a lot of Cat5 cables, which supports up to 100 megabits per second and might be reasonably okay for 1 gigabit Ethernet. But if you purchase a 10 gigabits per second switch for intensive use, make sure you get these cables, Cat6, particularly 6A. This will allow you to have physical transmission bandwidth up to 10 gigabits per second. Just, by the way, it doesn't make sense to buy a really high-speed switch and the cable limits the speed. Okay. Next in line is coaxial cable. And this picture shows pretty much the structure of such a coaxial cable. What it meant by coaxial is that they have 2 layers, concentric, and these 2 layers of coppers allow you to send signals. And because having 2 layers, it kind of allow the modulator, demodulators to easily cancel out the noises. And so data goes bidirectional on such a cable. A very primitive form of this coaxial cable was used by the legacy Ethernet. Yeah, by baseband it meant that the bandwidth is really, really small. Very low rate transmission, and it doesn't exist anymore. But then cable network picks it up, but enhance it somehow so that they can send multiple video programs over it, allowing multiple channels on the cable. And the cable exactly used by the cable network is HFC, the hybrid fiber copper cable. Oops. And the third is the fiber cable. Okay, so this is entirely glass-based fiber, and the bits are being sent as pulses, okay, like that. It works in a very high speed. You can go up to hundreds of gigabits per second. These high-speed fibers are oftentimes used by also the internet backbone, where lots of data are being exchanged. It's also used by the data centers, where there are always high volume data that needs to be stored or retrieved. These fibers, as we heard, Ftth, some of them slightly lower end is used for residential access as well. And they are very high speed, partly because it's very low error rate, because they are more resilient to white noises, background EM noises. The last media is the radio link. This one is very special. It is in fact the one that's used by all wireless and network access technologies. So what's listed here are just a few examples. Terrestrial microwave operating at about 45 megabits per second maximum. Wi-Fi, well, depending on the version, could be lower, 10 megabits per second, or half of 100 megabits per second. Wider area wireless access, 4G for example, goes up to a few megabits per second. 5G is now tens of megabits per second, okay, with the potential going higher than 100 megabits per second. And satellite radio, yeah, the bandwidth range spans wider with satellite, probably because of where the satellite is exactly and the technologies being implemented on that satellite. It can go from kilobits per second to 45 megabits per second. But one common feature is this. For satellite links, end-to-end delay will always be much longer than all these other wireless link access. Now, as to exactly how long the end-to-end delay is, it really depends on where the satellite is. For geosynchronous satellites, which sit higher above above Earth, the delay will get longer. The low altitude ones being lower, then shorter end-to-end delay. So, radio links, very special. Essentially, we are sending bits through these electromagnetic waves. There are no physical wires, so it's called unguided media. Data can go bidirectional, well, in fact, all directional. Which is a good and a bad thing. If you think about the propagation of these electromagnetic waves, it can be influenced by environmental effects. Having objects around, the objects can obstruct further propagation of the electromagnetic waves. And some objects might reflect, these waves as well. And the waves can be interfering with each other, coming from different sources, or even coming from the same radio source. It's called the multipass effect. So physical media, radio, it's very convenient, but you see the challenge of transmitting signals through these magnetic waves. You see also generally the wireless links, the maximum capacity usually lower than the guided media's capacity. Right, that takes us to the quiz number 4. And this is about the twisted pair cable, the Ethernet cables. So what I'm drawing on quiz 5 here on the left are 3 generations of Ethernet cable. First is Cat 5e, and then Cat 6, and then Cat A. You guys probably guessed Cat there stands for category. So category 5, category 6, category 6A. And these cables can differ in the frequency band they use to modulate signal. They can also differ in how they are packaged. The shielding around the copper wire, and how the groups of copper wires are arranged or separated. So you see the picture here on the table that 5E is a little bit primitive. You have 4 groups of these twisted pairs. Cat 6 there's like a separator in the middle. And in Cat 6A, for each group of twisted pair, there's I think some sort of metal shielding around each group. Okay. As a result, the capacity, okay, the bandwidth allowed for each of these cables gradually from older generation 1 gigabits per second to 10 gigabits per second. Okay, so if you have a 10 gigabits Ethernet switch, then you might want to choose the more recent generation Ethernet cable. Otherwise, your transmission speed is going to be limited by the cable itself. Okay. The different generations may also differ in terms of how long distance they will sustain. So 6A there is better than 6 in terms of the distance, allowing the cable to transmit data at 10 gigabits per second. All right. Yeah, it's a little bit different. Yeah, it is a little bit different. Okay. But you see, the difference is just that different generations of the cable, you use wider frequency band, which, let me see. So you answered week 2 quiz 4. Oh, I see what you're saying. Yeah, the cables. Okay, good. Very good, Xiang. Very good, Xiang. Please answer the questions that I have on the stream instead of the slide I actually uploaded here on Slack. Okay, I'll be updating that real quick. Okay, so here, given your knowledge here, looking at the table on the left, okay, and consider this home network. You have FTTH access to the internet, okay, but inside household, you have a really high-speed switch there, 10 gigabits per second. And you have link 2, it's an Ethernet cable connected to a video server. Link 3 connecting to, that's a NAS, okay, I think it's like a network storage for individual use. That's also high speed, 10 gigabits per second, and it's actually far away from the switch. Okay. And you have link 4 that's connected to a PC nearby. Link 5 there connects to access network, and it's a wireless access network. Link 6 is connecting to yet another PC, 10 gigabits per second PC. So Q1 here asks, in that network, what cable would you use for link 4? So that is the cable connecting to a 10 gigabits per second PC. And Q2 here, what cable for link 5? And oh, that is the one connecting to the Wi-Fi access points. All right, so gather your teammates and think about Q1, Q2. Polly is gonna update the picture real quick. Give me a sec. Let me see where. Okay, let me go back to the quiz so that you guys can read it, and I'm gonna update the Slack. Quiz real quick. Yeah, so the quiz is updated. Let me remove the old one just so that it's not confusing. Good. Let me check if it's updated. Yes, it is. And you know what? This is the quiz. You guys can actually work it through during the break, and we'll come back to discuss, okay, what the options are. So in the meantime, we take a 10 minutes break, and then we'll come back to the Slack and go over you guys' solution. All right, so let's come back to go over you guys' solutions. All right, so Team 5, Jiahong here said Cat 6 for the PC. Yeah, it is a PC nearby, and it's a 10 gigabits per second PC. So 6 seems to be a really nice option, right? Just good enough for the need. And one can, of course, use Cat 6A, right? So we are not limited by the cable, the transmission speed. But 6A is actually more expensive than the Cat 6. So yeah, Cat 6 seems to be a economical solution. For the Wi-Fi AP, very good. So Jiahong, Team 5, you guys know the capacity of the more recent versions of Wi-Fi very well. So AL2.11ax, the sum of the bandwidth provided there could exceed 1 gigabits per second. Yeah. So there's a good reason of using Cat 6 or 6A for it. And I don't know about you. I sometimes move my AP around so that a certain area in my home are better covered by Wi-Fi. So the distance between the AP to the switch can sometimes be a little bit more complicated. Okay, so we move the APs around from time to time. So 6A, I would say I agree with Team 5. It's a more flexible choice. Okay, but it will be a little bit more expensive, you see. Yeah, so AX or AD is certainly more than gigabits per second. It can probably be very close to 10 gigabits per second as well. Okay, AX, there are some of the newest APs use triple bands, and the sum of the bandwidth exceeds 1 gigabits per second. So guys, look it up if you haven't tried these yet. Let's see. I guess Team 1 Xiang here choosing Cat 6A based on similar reasons. Zhongting here. Cat 6 for the AP is making sense. Yeah. We don't move APs around all that often anyway. Amelia, 5E. Yeah, so well, in case you're using the lower end Wi-Fi APs, or actually most people use the regular Wi-Fi AO2.11 AC AP. In that case, 5E is perfect, okay, and very budget friendly. Yeah, that's a great choice. Wei Yuan. Yeah, so everyone chooses Cat 6 for the PC. That's perfect. There are many devices connecting to Wi-Fi. Yeah, there are, but be careful here. Okay, these devices connecting to the AP, if the AP is AL2.11 AC or AL2.11N, the maximum capacity of the AP is less than 1 gigabits per second anyway. Yeah. So 6A is way more than enough. 5E is actually enough as well. Okay, so wait. Yeah, I think Wei Yuan Team 3. Okay. I actually prefer using 6A, but that's because I have less concern about budget. But if you are choosing 6A because you expect more than 10 gigabits per second data coming in through, then this is a reason that doesn't quite address the choice. All right. That's wait. Oh, okay. So Amelia actually changed. Oh no, it's 5E. That's great. Xue Han, 5E is sufficient. Yeah. AL2.11 ends approximately this much, 400 to 600 megabits per second. All right. Very good. So Q1 here, very well done. Cat6 and Cat6e both sufficient. So the cable do not limit the switch, the demand itself. And as to which one you choose, if you are more budget conscious, then of course Cat6, right? If money is not an issue, of course Cat6e. So Xuehan here did a very good job, okay, giving out all the options. So let me give you this, 100 points. Youyu, Cat6 definitely minimum, and Cat5, 5E minimum for the AL2.11n or ACAPs. Yeah. Team 7, good. Similar to Team 12 there. Better since it's for AP. And to be safe, and depending on what kind of AP. You know what? In Polly's opinion, if I'm going to change the cable or connect devices to any switch, okay, nowadays I would just use the best cable possible, because making this, setting up the cable there, it actually takes time. And I actually consider time a more scarce commodity than money. So usually what I do is always go with the highest end cable. So I don't have to, I don't need to change the cable as much as possible. Use the 6A. So hey, so Team 7 here is probably thinking more like Polly, right? 6A, but what is the minimum? Very good. Okay, Sean is trying to provide the answer, to explain why. Okay. So did I mention what kind of AP it is on the figure? It is 11N, right? Yeah, AL2.11n. So 1 gigabits per second is sufficient. So 5E is sufficient. Okay. And you know what? The AP itself limits the maximum aggregated bandwidth. Okay. Yeah, so the data rate is maximum 400 to 600 megabits per second, just so that you know, Sean. 6A, and Keke here is saying, oh, if not considering upgrading devices in the future, 6A for all, I guess. Yeah. Oh, okay, so what you actually meant is that the minimum. 6 here, 5E here. Team 8, doors. 6 and 5E, cheapest, very good. So you guys get the idea. When you're choosing the cables, you definitely don't want the cable to limit the capacity of the switches. Okay, because cable is the cheaper one. The switch are more expensive. If you purchase expensive switches already, why? Okay, keeping the cable such that it limits the capacity of the switches. But then there might be multiple options choosing the cables, some higher end, some lower end. So in that, choosing among the options, it's basically how much money you have, how much you have in your pocket. Okay. Those who do not wish to upgrade again and again and again, every time you change AP, okay, every time you move the AP, every time you purchase a new PC, then you go straight to the highest end with the cables. Okay, good. All right, and that takes us back to the second half of the lecture. And we're going to talk about the core of the internet. Okay, in the core, the internet works in a very special way, following the principle called packet switching. Okay, but in this hour, we're going to talk about the general design principles. Okay, packet switching is not the only way of designing the core of a network. Circuit switching is another way. Let's hear what the core of the internet is and how circuit switching works. As access network is concluded, let's move on to the next component, the network core, which is a mesh of interconnected routers, as I'm trying to highlight here in red color. So you see a bunch of routers very well connected to each other. By well connected, let's see, if you count how many connections this router has to the rest of the internet. 1 here, 2, 3, and 4. 4 connections. Look at this one. How many connections? 1, 2, 3. Look at this one. It's an edge router, all right, but how many connections it has to the rest of the internet? 1, 2, and here, 3, 4. But if you look at a end system, such as this one here, how many connections it has to the internet? Just one here, through the Wi-Fi AP. Look at this PC here, only one. One very clear distinction between these routers to all these end systems is exactly in the connectivity, the number of connections they have to the rest of the internet. For routers, very oftentimes you see more than 2, including 2 connections. For end systems, just 1. And the reason that the routers oftentimes have more connections is because their role are just to transfer data. So it takes us to this very fundamental question. How do we transfer data in such a well-connected mesh network? In general network, communication network design, very general communication network design, there are 2 major mechanisms. First, circuit switching. Second, packet switching. Idea is quite straightforward. In circuit switching, from the source to the destination, let's build a dedicated circuit, and this circuit is going to be reserved through the entire time of communication, so we could just dump data in, and the performance is guaranteed. And this is the mechanism used by the traditional telephone network. The other technique, packet switching. Instead of allocating resource, creating a dedicated circuit, let's just use the entire link capacity and let's send data out no matter what. But we cut the data such that it's sent one chunk at a time. And to call such a chunk of data, we have this term called packet. All right. So it's almost like a package, but packet means also a little package. Okay. So we send data in smaller chunks, but use the entire link capacity. Okay. And to tell you ahead of time, internet or the data network is taking this packet switching approach. All right, and circuit switching a little bit more. All right, now let me elaborate circuit switching a little bit more. This is the familiar network, but this time we see on the network there are 2 circuits. The red circuit connects this end to this other end, similarly for the blue end. And to establish such a red circuit, which is also called a call sometimes, and the time it takes to set up such a call or such a circuit is also called the call setup time. Okay. And the reason that I need to mention that term is because that takes time, because resource reservation is required going from one end to another, which means this is the first link on the circuit. We need to reserve a certain amount of bandwidth to guarantee that data gets transmitted without any loss or delay. So you reserve link bandwidth for the call. Data is going to go through a switch. This is the first switch. On the switch, memory, CPU, buffer space will also need to be allocated and reserved. So that is what I meant by switch capacity here, to guarantee that the packet will not experience delay and not experiencing any loss. Similarly, for the second hop, for the third hop, fourth hop, fifth, sixth, seventh, and eighth. When all 8 hop link bandwidth switch capacity reservations are done, then you build a circuit. But then you see, as Polly was describing, this circuit here, resources are all dedicated. When data are being passed to, no delay, no loss. Really nice. And we call that circuit-like performance. That implies delay and no loss are guaranteed. Low delay, no loss, guaranteed. Similarly, for the blue circuit, and this is really nice because zoom into this segment. This segment here shared by the blue circuit and the red circuit. The two of them, although packet or data will be going through, but these data will not interfere with each other, not incurring delays to each other, and not collide to each other. No packet drops. These days, where we do online meetings a lot, having live YouTube channels a lot, we'd really like to have this circuit-like performance. This way, we don't have to worry that internet is gonna go bad and the live stream is gonna break at some point. Nice. Because for certain applications, we do need this type of quality of service. But you see, establishing the red circuit, we need 8 hops, and each hop takes some time to reserve resource. So there's quite a bit of call setup time involved. This is the downside of circuit switching. Another downside is this. The way we are allocating or reserving resources over the entire path from the two ends of data communication is more. We divide the link bandwidth into smaller pieces. We divide the switch capacity also into smaller pieces. And once we do that, we allocate individual pieces or combinations of pieces to an individual circuit or individual call. But once you do that, if there are no data being sent between the two ends, that piece of resource will then be idle. If you think about it, in a way, it's a waste of resource. If the two of them ask for resource and a call established, but they're sitting doing nothing. So not very good utilization of resource. So this is the second disadvantage of doing circuit switching. Now, speaking on dividing link capacity into pieces, there are multiple ways of doing that. First one is called frequency division, the other time division. This is the second time we see the term FDM. Where did we see this? Yeah, cable modem. We divide cable modem capacity. We divide the cable network link capacity into what? Pieces by the frequency band. This is a very different flavor. Okay, it's dividing the link by the time. Let me illustrate. The example on the top is doing FDM, where we divide the entire frequency band there to 4 users in equal division. So, full frequency band, 1/4 to the blue user, 1/4 to the green user, to the yellow user, and the pink user. TDM works this way. Instead of dividing the frequency dimension, that's divide, okay, in the time dimension. So with these time slots, we allocate the time slots in a rotating fashion to the 4 users like this. Blue, green, yellow, pink, blue, green, yellow, pink. Yeah, it's rhythmic. That is exactly how TDM works. With a good rhythm, with well-synchronized time, the 4 users can send data one after another. Very orderly. If we have more than 4 users, how do we do that? You see, we could further refine the division into, for example, A parts. That way we can accommodate how many users? A users. Similarly for TDM. All right, so let's take a look at an example calculating the transmission time using such a circuit switching principle for the core of the network. So make sure you pick up circuit switching and how it works. Let's see if we can work out this problem together. The question asked is, how long does it take to send a file, this big, from A to B over a circuit switch network? And in this network, all the links have the same capacity, 1.536 megabits per second. And each link is divided to 24 parts using TDM. And meaning that circuit between A and B only gets 1 slot. And the presumption is that to establish the end-to-end circuit between A and B, it takes this much time. All right, so how long does it take entirely to send the whole file through? Let's work on it. All right, so let's do it live now. Let's see. The bandwidth is 1.536 megabits per second. And A gets only 1 of 24 of the bandwidth, 1/24 of the bandwidth. And how much bandwidth did A get effectively? Well, give me a second. I do have a calculator here. 1.36. Yeah, so we get 0.064. That will be 64 kilobits per second. And we know the file size is this big. So how long does it take to transmit these many bits over effective bandwidth? 64 kbps, 10 seconds. And plus the half second to establish connection, then we take 10 seconds to transmit the file. So altogether, 10.5. In a circuit switch network, if each host gets only 1/24 of 1.536 to send 640 kilobits, 10.5 seconds. So that's the idea of the circuit switching. And such a technique is used, such a design principle is used, in fact, in the telephone network, the very old wired telephone network. Oops, sorry, let me come back here. And we move on to the next principle, the principle that is used to design the internet. And let's hear out how packet switching is working. Now let's discuss more about packet switching. The mechanism is very simple, right? We simply cut the data into small packets. And as the link is available, pass it out. So each of these small packets will go on the link in full bandwidth. So if you consider L being the size of the packet length, and R being the link bandwidth or the link rate, the delay, this being small, this being large, to send a packet very small. This is one advantage. And then think about this: if you get 2 users, A and B, both are generating data and both are sending these packets out. If A is idle, not sending, and B comes up with data, B can send out, no problem, and in full link bandwidth. Similarly, if B is idle and A has data, no problem sending out. So there's no such a situation in circuit switching when B allocates all the resource, gets all the resource, and A having data to send, but A didn't get any resource as a result. B sitting idle, occupying all the resource, and yet A having lots of data wanting to send, not getting anything. Okay, so there's no idle ways there. Last is maybe a little bit less obvious. You see, bandwidth is used as full, so there's no need of dividing the link bandwidth into pieces. So the mechanism is also simple. Okay, being simple, there's no idle waste, and there's no call setup, resource reservation process required. Okay, packet switching can potentially be very efficient, especially for short data streams. Think about the resource reservation delay, the call setup time. It can be pretty long, and if you have very short data stream, then hey, the overhead relative to the entire need of sending data is high. So you can probably imagine now, data network, internet. At the beginning, we were just sending really short emails. It doesn't make a whole lot of sense just to send an email and you go all the way to set up a circuit. So another advantage of using packet switching is also because of the user demand. Now let's look at what's wrong with packet switching. First of all, we will have resource contention because there's no reservation mechanism. What if A and B, they all have a lot of data to send, so the resource demand is beyond the available resource. So we call that situation network congestion. In that particular situation, packets will have to queue up at these routers and wait for link queues. So you see here, wait, the key word. Delay here to transmit the packet is short, but there could potentially be way that is a little bit uncertainly long. Okay. And hey, packets will get queued. What if there's not enough space in the queue? Packets also get dropped. So in packet switch network, we do have substantial delay. We could have substantial packet losses. One big disadvantage. Another disadvantage is here. This one is a little bit subtle. In packet switching network, there's no circuit being established. The way we send packet is that you forward it out on the link. The next router will need to pick up everything. So you need to wait until the entire packet is received. The next router will need to receive the complete packet before the router can further forward the packet. So this is called store and forward. So the router action there, passing packets, is store the packet first and then forward the packet next. So this mechanism here is determining how packets are moved, okay, one hop at a time. Meaning you have one of these, L divided by R, every hop, every router. All right, so you kind of see the contrast between circuit switching and packet switching. Circuit switching, no delay, very predictable, no packet drop. Packet switching, you get delay and sometimes unpredictable, and you get packet dropped. That means packet never get to the destination. But on the other hand, circuit switching does have this issue with a call setup time, and the resource might be left idle in case there's no actual data being sent. On the other hand, packet switching, better utilization of the link capacity, of the network capacity. Okay. So circuit switching, you now see a little bit, hey, it's actually great for a voice. Okay, that's why a telephone network is using circuit switching as a design principle. But on the internet, originally we just send emails. Okay, later on we download web pages. Okay, all these are actually quite short. Okay, as opposed to phone calls usually go a little bit longer. So depending on the data we are transmitting, the network design could be based on different principles, right? And next video is just to develop a little bit more and explain a little bit more packet switching and focusing on the downside. So here let me illustrate the store and forward effect to the end-to-end delay. So consider this scenario. The source is over here. Okay, user typing up things and generating these small packets, 1, 2, 3. One router here in the middle and receiver on the other side. And each packet here the user is generating is L bits long, and the link bandwidth is R BPS. So you see, to send this big packet over the link at this speed, this is the amount of time that's required. And on a packet switch network, we need to store the packet entirely before forwarding. So entire packet needs to arrive at the router before it can be transmitted further. The end-to-end delay will be what? 1L divided by R for this hopping. Because this guy, to send it out, it requires L divided by R. This router here receiving it waits until all is received, and then what? Send it out again. That's another L divided by R. So if L is 7.5 megabits per second, R is 1.5. You see, each hop, 5 seconds. 2 hops, in this case, how long? 10 seconds. 3 hops, the longer, the more hops you have, the delay of sending the packets longer. This is different from circuit switch network. Bits can be streamlined. Okay, there's no need to store a bunch of bits first before forwarding it. Okay, that is saying that each bit arriving here gets out quickly, so there's no hopping. It's just the propagation delay and the transmission delay, L divided by R, from the first hop. This side is to illustrate congestion. The scenario is A and B, 2 users generating packets, A generating blue packets, A generating green packets, and B here generating blue packets. And you see these packets are generated as user A and user B are typing things up spontaneously. So green and blue, they will kind of bunch up or multiplex in a random order. Okay. Unlike in TDM, time division multiplexing, everything goes rotating, rhythmic. And this, okay, having some sort of spontaneous behavior in it is statistical multiplexing. Okay. So on packet switch network or on the data network internet, packet kind of multiplex to each other randomly, spontaneously, depending on how they are generated. Now let me draw your attention here. The router. You see packets in case the outgoing link bandwidth small, and incoming link here, this is 100 megabits per second Ethernet. This is only 1.5 going out. Chances very high, A and B, if both of them actively generating lots of packets, the packets will have to wait here in the queue before they get the link queues. And if there's not enough space here for the queue, The next one, the green one coming here, will need to be dropped. But there's no memory space to hold. And those packets waiting in the queue, yeah, it depends on how long the queue is as they comes in to the router. The queuing delay can vary. It can be a little uncertain. But transmission delay, the time it takes to go on this link is always the packet size divided by what? 1.5 megabits per second. And we use the full link bandwidth. So transmission delay here is very easy to get. All right, so I hope that illustrates well. Delay can be long, unpredictable, and potentially you have packet loss. Now let's compare CS and PS a little bit more formally. Here, let me use an example to illustrate. Packet switching actually outperforms circuit switching when there are more users and each of these users are not exactly very active, sending short messages only each time. All right, so scenario is very simple. Okay, we do have a network of end users and they're behind this router. Going out of the router is a very low bandwidth link, 1 megabits per second. And each of the users is behaving this way. When they're active, they do need a lot of bandwidth, 100 kilobits per second. But they're only 10% of the time active. In a circuit switch network, in order to satisfy these 10 users, and each at maximum requires 100 kilobits per second, so we reserve 100 kilobits per second to each of the users. And how many users we are allowed to reserve bandwidth? This is 1,000 kilobits. So we can only allow 10 users, okay, 10 circuits. But in packet switching, you see, the users are only active at 10% of time. Consider this scenario. If we have 35 users, right, the only situation that these 35 users will have trouble sending data out is when there's at least 10 users being active at the same time. So what is the probability of these 35 users and more than 10 of them being active at the same time? If you do the calculation, you'll see that it's very low. So 99.9996% of the time, in packet switch network, 35 users will do well. No trouble. So if you do have a lot more users and each of the user needs just a small portion of time to send data, which one would you pick? Circuit switching or packet switching? It's quite obvious, isn't it? And oh, by the way, anyone here knows how to derive this value? The probability of 10 of the users being active at the same time, given the active rate is 10%. All right, so those who know how to derive the probability 0.0004, please do post it in, let's see, channel Ask Us Anything. You receive extra credit for that. Good. And this brings us to the last part of the lecture today, quiz number 5. Let's try to make choices also. Okay. Circuit switching, as you heard, okay, you reserve a portion of the bandwidth for the data and strictly for a connection of data. Okay. It's almost a little bit like when we are transferring water through the pipelines. Okay. So there is a dedicated pipeline from the top, okay, to the faucet, allowing water to go through. Now, packet switching thinking is a little bit different. Okay, we break the data into packets. Okay, sometimes we call these packets messages. Okay, and then we send the packets out, messages out in a mixed way, and hopefully they pass the network to the particular faucet that they are designated for. Okay, so it's almost like putting the water in buckets and then passing the buckets around. You see that the transmission model quite different. So Q1 here is asking, all right, so let's consider vehicular network. So in human society, right, we move all sorts of vehicles around. Cars are a kind of vehicle. Trains are also a kind of vehicle. Okay, so now based on how you understand we move cars around, do you think the car network is based on circuit switch network or packet switch networking? Okay, and why? Okay, and for train network, do you think it's more circuit switching or packet switching, and why? Q3, which one do you like better? Circuit switching or packet switching? Okay, and this obviously is personal. Okay, as long as you can justify why you like one over another, then you're fine. It's 12. We have 10 minutes to the end of the lecture. So let's do this real quick. Okay, gather your teammate and type up your solution as soon as you can. Okay, before 12:10, we'll see how many teams manage to provide your solutions. And the rest of the teams, of course, feel free to work on it if you need more time. The due time of the quiz solutions for this week is the Saturday of the week. Good, so let's go on and start working on this. What do you think? Car network, is it circuit switching or packet switching? Train network, circuit switching or packet switching? Okay, among the two, which one do you like better? Okay, so I actually see team 1 here who managed to type up the answer real quick. So first for Q1, okay, team 1 thought car network is more packet switching. Because we can use the row whenever they want, and there are probability that a traffic jam can happen. Oh, congestion. Yeah, it is more like packet switching, because packet switching is the one having congestion, unpredictable delay. Too many cars, right, merging onto the same road that doesn't have enough capacity to let all the cars through. Yeah, I think that's a very strong evidence of the car network, the car moving in the row network. Okay, the street network is packet switching. Okay, Makes sense. Makes sense. Okay. Let's see. Circuit switching. So train network is more circuit switching for team 1. Let's see what the reason is. Oh, because the train track is a little bit more like a pipeline, right? Of waters. The waters will be transported through the pipeline, just like the train tracks are dedicated for the trains. And these railways, the tracks, they are connected and fixed. Okay, at certain points they will be also switched, right? Yeah, so when it's at the scheduled time a train needs to cross over, the switch change, and then the railroad is like, you set up a call, okay? You set up a whole pass, okay, before the train start working on it, going on it. Okay, so thinking that way, yes, train network is indeed circuit switching. Yeah, so certainly not all the trains can get on a certain track when the train is scheduled to go through the track, right? And guys, I don't know if you guys been to Pingxi. Okay, that's an area where we still have these very old trains, very old-fashioned tracks. Okay, the tracks are actually narrower. So they still use a token there to ensure that there's only one train going on a segment of the track at a time. So how the train system works is in fact very interesting. At places you see that it resembles the internet. And at places you see that it resembles the telephone network as well. So train network, based on Team 1's explanation, it does look a little bit circuit switched. And Team 1 prefers packet switching because it grants more speed. Yeah, it grants more speed for each connection at a time, isn't it? And okay, Huixing started typing. Feel free to go on. Then let's go down the list. Team 4. Okay, so Team 4 is like Team 1. Car network is a little bit PS. Okay, there's no fixed route. Okay, there's no reservation. Yeah. CS for the train network is a fixed destination, fixed schedule. Yeah, so it's like reservation based. Team 4 thinks both are great. Okay, that's a good answer. Depending on the needs, perfect. You've got it. If you wish stability, long-term sustainability, circuit switching. Okay, but if you are having small amount of data, short connection, flexibility, then packet switching. Very good, very well done. Very well done there. Okay, monkey for Team 4. All right, Zhao Qi representing Team 2. Packet switching, circuit switching. I like short answers as well. And Team 2 prefers packet switching. More flexibility. A higher transmission rate potentially. Shorter amount of time to receive a response. And allow more users, right? You see earlier we were trying to use an example to compare. With high probability, we allow more users. Team 7, also very short, get to the point. Depends on the data size and how many users. If delay is not acceptable, then circuit switching. Okay. Team 8, car network, packet switching principle. And the car is more like the individual packets. I see. Train is more circuit switching. And you prefer the car network, packet switching. More flexibility. Yeah. You know what? For a network where the resources are limited, it's always a better thing to have more flexibility. So internet, based on how we're using it, yeah, the capacity is limited. Definitely, we would like to have more flexibility, and packet switching definitely a really nice choice to begin with. Okay, so the internet engineers back then, I think in the 1960s, the vision is quite nice and good, isn't it? Okay. And internet did grow so big, and we are accessing it every day, every second pretty much. And you know what? And that's all the time we have. Team 5, 6, 3, 10. Yeah, I'll go over all you guys' solutions in detail. Okay. In the meantime, feel free to go on catch lunch or meet friends or run to the next lectures if you do have lectures or meetings during lunch hour. Starting from now, it's the office hour. Okay, so I'm gonna stay on for a little bit longer to go over 5, 6, 3, 10, the rest of the team solution. Okay. During the breaks and during the lecture, there are also some students asking questions. So what I'm gonna do is they actually ask in a private channel. I would post them to ask us anything. So you will see the question, and you will also see Polly typing up solutions or answers to those questions. Okay, good. With that I say bye for the lecture. I will see you next Wednesday. So feel free to go. And so let me do this. Bye-bye. All right. Okay, bye. Yeah, so by the way, we might not have we might not have enough time to answer all the questions you guys have during that day. Yeah, so it's okay. We can take it offline. You will still see the questions being answered. Okay, bye. All right, so we're here. Let's see, team 5. Okay, packet switching for the car network and circuit switching for the train network. Yeah, you also like the flexibility of the packet switch network. Okay, bye. And Shen Hao, packet switching, because every car uses the same road, but sometimes there are too many cars. You have to wait. Yeah, contention is a major characteristic of a packet switched principal network. So let's see, circuit switching, rail is allocated to a specific train at a particular time. Yes. Okay, bye. Bye, Keke, Pi Team, Yu Shou, Catfish, Wei Xiang, Sean, Jia Hong, Xue Han, and Amelia. Let's see, Team 3, Wei Yuan. Car network is more like packet switching because roads can be used by every car, which is like packet. Yes, it is. It is. Okay. Train network more circuit switching, I guess. Switching. Railroad exclusive for trains. Yeah. Hi, Catfish. But be careful. Whatever you say, it's gonna be streamed out as well. Would you prefer that I end the stream and then you ask questions, or you don't mind asking questions and talk on fly like this?
I prefer waiting for
Sure, sure. Okay.
after the stream.
Yeah, okay, good. Stay on for a little bit longer because it's office hour. Okay. Um, let me just go over the quiz solutions and I will come to you. All right. Packet switching because it's more efficient, flexible. Team 10 here. Cars more like packet switching. Yeah. Interesting. Interesting. Okay. Well, that's another way of saying the flexibility. Yeah. Okay. You can go anyway and dynamically. So each car, okay, even though they go to the same destination, but they can go through different roads, okay, different routes. But in a circuit switch network, once you establish the connection, every train go on for that road, that route. Every train go on the same route. Yeah. Train circuit switching can choose our time. Yes. It's deterministic. Yes. We prefer packet switching because flexibility. And there might be things we can do to avoid congestion. Good thinking. Good thinking. And 由于 Team 14. Cars can go on the roads just like packets. It's a little bit more flexible, more freely. Train network is mixed PS and CS. Very interesting. Different trains need to use the same railway in different time, but occupy one. It is. Okay, so the later part makes it look more circuit switching, but multiple trains might go through the same segment. Okay, it's a little bit packet switching, right? So you share resource to some degree in a train network. Very well done. Very good observation there. Because there might be many people using the same time. Yeah, generally these days, we prefer more flexible solutions such as packet switching. Okay, very good. All right, so that's all for the stream. Polly's gonna hang around the Google Meet session. So if you have questions that you want to ask in real time, just call in. Okay. So let me end the stream for now. And bye for those who are still online.